Roman numeral 5 is on Newton's laws. And yes, it is a little bit longer of a section than usual, but I'm going to try to go through it quickly. And then also we're going to have some demonstrations in class so that we can review the material as well. So let's get started. Newton's first law states that an object with no net force acting on it remains at rest or moves with constant velocity in a straight line. I wanted to point out this word net means total. So we're going to look at the total amount of forces acting on an object rather than just one force at a time. This also is called the law of inertia. So to define inertia, that would be the natural tendency of an object to resist any change in its state of motion. And this whole year when we've been talking about mass, that's a quantitative way to measure an object's inertia. So for example, if an object is really, really large and it has a big mass, then its tendency to resist any sort of change of motion is going to be more difficult than an object with a smaller mass. Earlier, when I mentioned no net force acting on an object, we have an example of you sitting in a chair. So right now, you have the gravitational force pulling you downward, and perhaps you're in a chair, so that chair is providing a normal force that points upwards. And we can indicate direction of our forces by including those plus and minus signs. So I chose up to be positive and down to be negative. So even though there are forces acting on you, if we combine and add those together, since they are in different directions, we actually end up subtracting them, and that turns out to be a total of 0. So this would indicate that there is no net force acting on you while you're sitting in the chair, even though there are different forces that are present. So now that we've talked about what no net force means, let's discuss the second part of that first law. So when there's no net force, our forces are going to be balanced. That gives us two options. One, the body or the object can be at rest, which means it has 0 velocity. The other option would be that the object is moving with a constant velocity. So think about what this means for the acceleration of an object. If an object is at rest, does it have any acceleration? No. Also, if an object is moving with a constant velocity, so that means it's not speeding up, nor is it slowing down, that also means that there's no acceleration. So both of these, in terms of the acceleration of an object, would be 0 in both of those cases. So we can take all of this knowledge and put it together and write a shortened version of the first law, which would be if there's no net force, so if the net force equals 0, so remember, you can still have forces, but they would cancel each other out. So if the net force is equal to 0, then we can say our acceleration is equal to 0. It's just an easier and shorter way than having to state that the body can be at rest or move with constant velocity in a straight line. So remember, the net force means the total forces added together, and then another way we can write that is the sum of the forces. So remember back in chapter 1, we had a couple of those mathematical notations. This would be a case where we could use the sum. And then also you might see this other word come up. If the sum of the forces is 0, then the object is said to be in equilibrium. So that's another way of stating that there's no acceleration as well. So I've got some slides for you. This is just a way to restate Newton's first law. And then here would be an example with a golf club. The golf ball is at rest until it's acted on by an unbalanced force, which would be the club. So as long as no forces come along and apply something sideways or horizontally, then that golf ball is going to sit right there and it's going to stay at rest. Another one might be for a car crash. If we talk about an object moving in a straight line at a constant speed, then it's going to continue to move in a straight line. So for example, if we have the car bumping into a wall, then if they were not wearing a seatbelt, the passengers would continue to move forward, even though the car itself is actually stopped. Now we're going to look at Newton's second law. Pretty much it's going to be the opposite of the first law. The first law stated there was no net force, so there was no acceleration. Now for the second law, we are going to have a net force, and we talk about that in terms of an unbalanced force. So when that occurs, the object will be accelerated. So now we're going to have an object either speeding up or slowing down. And this acceleration is what's going to distinguish this law from the other two. So let's talk about it in a little bit more detail. This acceleration will vary directly with the unbalanced force, and it's going to be in the same direction. Remember that force is a vector quantity, so don't overcomplicate that. If something is pushed with a force going forward, it's going to accelerate in the forward direction. The harder I push, the more it accelerates. Those are directly related to each other. They behave in the same way. However, when we compare the acceleration to the mass of an object, those are going to be indirectly or inversely proportional. So think about a really, really large 18-wheeler, say, on a highway. It's really, really big, so it has a difficult time accelerating. It has a large mass and a small acceleration, versus, let's say, a sports car has a really small mass, but it can accelerate very easily. So when we look at Newton's second law, the acceleration and the mass are going to behave in opposite ways. So we call that indirectly or inversely proportional. And going back to chapter 1, when we had those mathematical notations, we used the little fishy symbol, and we talked about how that was a way to discuss proportions. So if I look at the acceleration, I would say acceleration is proportional to the force. They are directly related to each other. The acceleration, on the other hand, is proportional to the inverse of the mass, so I would write that as 1 over m, and that lets me know that these are going to behave in opposite ways. Now we can put all of these together when we compare the acceleration to the force and the mass and come up with an equation. So the equation for Newton's second law is going to be F equals ma. And technically, the force here is going to be F net. And remember, another way that I could state that would be to say the sum of the forces. So if there's more than one force present, we want to add all of those forces together, and that total is what's going to equal mass times acceleration. And I want to take a moment to look at the units. You should know by now that mass is measured in kilograms. And then we would multiply that by the units for acceleration, which I hope you remember would be meters over second squared. Now, if we combine those into one fraction, we would have kilograms times meters on the top and second squared on the bottom. That's kind of a large mouthful to say for a unit, kilogram meters over second squared. So this was shortened, and that combination of units is now called a Newton, and it was named after Isaac Newton since he did a lot of work in the area of forces. This part down here that I covered up earlier, don't worry about that. These are going to be demonstrations that we do in class, and we will go over these notes as well. So just bring your notes with you, and we will talk about those together. So just to review, Newton's second law is going to be the only one of the three that has an equation, and it's F net equals ma. An example would be a train with a very large mass requires a lot of force in order to stop it. Okay. And then also, the greater the acceleration or mass of an object, then the greater the force will be required to change its direction of motion. In other words, to make it accelerate. Newton's third law. Sometimes this one is also called the law of action-reaction. And the law is stated, every force is accompanied by an equal but opposite force. So remember that force is a vector quantity, so when we say an equal but opposite force, equal refers to the magnitude or the size of the force, and then opposite refers to the direction. Another way that you may have heard Newton's third law would be for every action there's an equal and opposite reaction. So if we have the force of object A on object B, that's going to be the opposite or the negative force of object B on object A. So we have an example of a bird flying. When flying, the bird's wings push down on the air, and in return, the air pushes upward onto the bird. And then we used this example earlier, would be a person sitting in a chair. So in this case, the force of gravity is pulling downwards, and then the force of the seat, which would be the normal force, is pushing upwards. So the person pushes on the chair, with the same amount of force as the chair pushes back on the person. So just to summarize, Newton's 3 laws, you can think of the first law as the law of inertia. Remember, for that one, if there is no net force, then there is no acceleration. Next, our second law would be F equals ma, and for this force, it is also the F net, or the sum of the forces. So you want to take into account all forces that act on an object, and that would be equal to mass times acceleration. So remember, the first law, the forces are balanced. The second law, the forces are unbalanced. And then the third law is the law of action-reaction. So that's it for right now. Remember to bring your notes with you because we're going to have some demonstrations in class about inertia, and we will refer back to Newton's 3 laws when we do these demonstrations.